Now we've got a lot to cover today in numerical methods for partial differential equations. And there is the assumption we are going to be running that you know everything that is required about partial differential equations. Okay, so I want to believe you know all that there is to know about partial differential equations. So we could just dive in to the methods for partial differential equations. So for us to begin, I'd love us to interact a little. What do we understand by partial differential equations?
Partial differential
Now go ahead, please.
partial differential equations are equations. Hello, sir.
Yeah, we can hear you. Go ahead.
I can't. Okay. Partial differential equations are equations that defined in functions of x and y. So we keep one of the variables constant and differentiate with respect to the other one. Then, and the second aspect, we keep the second constant and differentiate with respect to the first.
So we differentiate x and hold y constant, and then differentiate y, and then hold x constant. Okay, thank you so much for that contribution. We need some other views. What do you understand about partial differential equations? The most important thing here is that we have two independent variables, right? From Engineer Joel's description, okay? X and Y. And then we have to differentiate one and hold on to the other as constant, and it means there is some partial differentiation going on, isn't it? So we need some other contributions before we move on. Okay, so I think Richard started this class. So can Richard Irabor tell us, what do you understand about partial differential equations? Why are they important to us? Why should we bother ourselves about partial differential equations in engineering? I think that's what it is. So who else? You can unmute and talk to us, please. We have Ibrahim Lima, Isaac Obe, Rachel Mama, Kuku Michael, Nancy. So who's going to help us out? We have Adeboye Ogunlami, John Adeshino. We have quite a number of...
sorry, I was trying to unmute my system. So, I think for me, to my own understanding, just like it's almost close to what Joel has already said, is containing partial derivative of the dependent variable, maybe one or more, with more than another one independent variable.
Also, okay. So why is it important to us in engineering? Why should we bother ourselves about partial differential equations? Why should we even consider them? Why talk about numerical methods for them?
Well, it's more significant probably because in terms of simulation and optimization of complex systems, so we might actually need it for that.
Okay. Now, there's one candidate that have been very, very, very active in this series, Farouk Agbola. Can you please tell us, what do you understand about partial differential equations?
So I think want to align with what Engineer Joel said. The partial differential is equation with where we hold y constant and we differentiate with respect to. Will I say we say y? We say we hold will I say the dependent variable constant with respect to other, will I say one or two other independent variables. I don't know if I'm getting it right.
Okay, that's awesome. But now, do you have any practical application in mind where we see this partial differential equation in electrical engineering?
None is coming to mind now, sir.
Okay. Yeah, well, we'll come to that. So, can anybody else in class
Okay,
help
sir.
us?
So I think that for all these that we've done, we are considering if a particular.
Go ahead, please. Hope we didn't lose that video. Okay, it's like connection issues.
Hello, sir.
Okay, go ahead, please. We can hear you now.
So if I could just try, I think it is used in signal propagation.
In signal propagation. Okay. Yeah, signal propagation. Awesome. Okay, so we are going to be looking up this technique.
Hello?
Yeah, hello. You still
Okay.
have something you want to tell us?
Yeah. Also in addition to that, we talk about heat waves, the fluid flow, and other things like that. So then we also look at the fluid dynamics. So all those complex, majorly the complex aspects of
So
engineering.
if we talk about the heat equation, for instance, then what do we call X? What do we call Y? Are they still X and Y variables? Is S and Y still the independent variable, or are X and Y the independent variables we need to consider still when you now talk about heat wave? Someone mentioned wave propagation, mentioned heat equation or something. Okay.
Also using a control. So using control for multiple output systems.
Well, I didn't get that. That wasn't quite clear. You know, I didn't really get what you said.
So using control for multiple input, multiple output systems.
Okay, in control systems, right?
So we know for the X, we have the input and output. So
okay, just a multiple input, multiple output system. Okay. So why do we consider this in multiple input, multiple output systems?
Because we actually want to have a stability in the system, so able to tune the input to actually get to stable output. So once you have a feedback and the right.
That's awesome. That's great. And one thing I'll just add to this, when we talk about multiple input, multiple output systems, we are literally relating with the variables in the spatial domain, right? So now that we relate with these multiple input, multiple outputs in the spatial domain, so it means our X may be from X1, S2, X3, all the way to Sn. So these are all independent variables, right?
Yes.
This time. So, and at some point, we now have to relate X1 with respect to X2 to Xn. And then that brings us back to partial differential equations, just like Engineer Joel mentioned earlier. So we want to differentiate one of these and hold others constant, right? And then we'll keep going. So excuse me. Excuse me. Now, it means that the partial differential equations is very, very important in terms of describing the multiple input, multiple output systems largely because we are not dealing in the spatial domain. And dealing in the spatial domain means we now have a number of independent variables we have to deal with. Okay, I think that is what makes it interesting. Now, if you remember well, when we made mention of ODEs, we also try to distinguish between ODEs and PDEs. So the ordinary differential equations, we said, well, they involve just one independent variable. And that independent variable could either be time or space. Okay, so it means that we have to deal with this differential equation strictly with respect to one of these independent variables. So we could say the whatsoever dt or the whatsoever dx. Okay, so it means that the independent variable we now have to consider for the ordinary differential equations is just one independent variable at a time. But what happens if we now have to compute a system where we have to deal with both independent variables at the same time? So sorry for that. So now for the PDEs, we now have to deal with systems where we have to consider the partial derivative with respect to these multiple independent variables. Now, having X and T just tells us that we are dealing in the spatial domain and also in the time domain. So one may ask, what if we have three independent variables? So what is the third independent variable going to be? So we could actually have X, Y, and T, where X and Y are still some spatial variables. And T is still the time domain or time variable. Okay, does this make sense at all? Does this make sense? Hello, does this make sense?
Yes, it does. It does, sir.
Okay,
It
now,
does.
okay, perfect.
Okay, we can hear you, sir. Thank you.
Okay, so now we now want to consider these systems, okay? And we realize that in engineering, we get to, by default, come across certain systems where we have to deal with their spatial relationship. And at the same time, their variation with respect to time. Okay, and if you recall so well, you realize that Maxwell literally boxed us into that corner when we now get to talk about the wave equation. Okay, so we want to tell, well, this wave is propagating with respect to time. There's a variation, but there is also the space of polarization. Okay, and we now realize that we may not be able to interpret the relationship of this wave with respect to this alone. Okay, now, well, so as I was saying, when we now have to deal with such instances, we now realize that the ordinary differential equation does not give an absolute description of what we may say characterizes the performance or the behavior of such a scenario, okay? Because now we realize that we are now beginning to describe these parameters with respect to some coordinate positions, okay? While we are talking about the plane of polarization, for instance, if we have to talk about the electromagnetic wave activities, we now realize that we have the E field and the H field, right? The magnetic intensity and the electric field intensities. And we say they are perpendicular to each other. And both are also perpendicular to the plane of propagation. So you now see that we have something like this. Okay. So now how do we relate with all of these? And then we are not particular about the direction we have, especially for your transverse electromagnetic waves. Well, I understand some of you are taking electromagnetic waves. Now, whether you're in power or control electronics or communication engineering, there's one thing that brings us together is the electromagnetic waves, right? So you still play with it when you deal with machines and transformers and all of that. You still have to play with these principles, the Ampere's laws, the Faraday's laws, and all of those, okay? But at some point, you want to analyze what is happening to the flux, okay? So when you now have to analyze that, you also have to analyze this with respect to the coordinate system, okay? So in relating this with the coordinate system, then you have to interpret what is going on, okay? And then we now want to begin to establish the relationship with respect to these independent variables, and then that brings us to partial differential equations. And for us to go any further, I would love us to just run through a brief background, because the idea is, fine, we want to solve partial differential equations. So we also need to understand what these partial differential equations are and what are the types of partial differential equations. Now, some of you may have heard of hyperbolic partial differential equations, parabolic partial differential equations, and also elliptic partial differential equations. So we'll try as much as we can within the space of time to run through this, and then also look up some of the numerical methods that we can use to address these problems. And beyond that, well, the numerical methods that can be used we won't be able to cover all here. Yeah, literally inexhaustive, let's put it that way. So, but we'll try to touch the little we can, then while we leave further investigation to the class to sort depending on the problem you want to address. Okay, now, before I move any further, I want us to look up the classification of problems, okay? Classification of physical problems. So when we look up engineering problems in general, all engineering problems, what we get to solve in engineering, whether you're in power, in control, in communication, in electronics, even mechanical, regardless of the engineering discipline. Now, who can tell us how these problems are categorized? Okay, so I think just a little interaction. So I want you to share your thoughts. Can Lawal A. Muhammad, share with us in terms of classifying physical problems in engineering? What are the categories? Can you unmute and share with us your thoughts? I know we already covered some in this series, so we just want to summarize and see how we'll be able to move into discussing, describing the partial differential equation problem. Okay, so Emmanuel Adebayo, you want to help? Okay, Lawal is up. Okay, go ahead, please.
Good morning, sir.
A very good morning.
Hello, doctor. Please, can you come again with the question? I heard you mention my name.
Okay, yeah.
Sorry, sir.
We're looking up the classification of physical problems in engineering. So now we want to see if you'll be able to probably tell us how the categories when we classify physical problems in engineering. So we've talked about some of the problems that could be ODE related, just single independent variable. Then we have some problems that could have multiple independent variables. So what do you think? So can you help us out? Or you need some time to think through it? Okay, let's give you some time to think through it. So, Celestine. So, can Celestine help us out?
Okay, Doc. Good morning.
Good morning.
So,
very good morning.
Are we talking about the physical problems here? Concept of field friends, like object physical studies.
Okay.
Human nature related problems.
Okay.
Like when you are modeling, what the instrument you want to use.
Okay.
How will you apply it? And the possibility of creating some of the new substances within the properties. Okay. So that's what I'm thinking about.
Okay, okay, that's fine. I think you just gave us a general overview, a broad overview, okay, of what these physical problems, how we could model them. Awesome. Now I'll just go a little. I'll try to be a little specific this time. So when we try to analyze some problems, I know we made mention of some problems that are boundary value problems. And these problems are usually referred to as equilibrium problems. We also have a class of problems we call the characteristic value problems. We also call them the eigenvalue problems. And then we have a third group that we call the initial boundary value problems, which I think one of us mentioned that while we were trying to summarize the introduction to this course, the propagation problem. Now, from study, we've been able to realize that bulk of what we get to do or address as problems in the engineering field fall within these three categories. Okay, so I think we'll try to explore them one by one. So from the equilibrium problem to the eigenvalue problem, and then to the propagation problem. And then afterwards, we now figure out how this relates to the partial differential equation mathematical discipline, let's put it that way. Okay, so when we talk about the equilibrium problem, we are literally trying to figure out what we call the steady state problem. Okay, so these problems are problems of steady state, okay, in which the equilibrium configuration of, say, some phi in the domain D is to be determined by solving the differential equation, okay? And this, we could designate that if the differential equation is described as L of phi being the same as F, where in this case, D is the domain and is subject to some boundary conditions, say B sub I of phi being the same as G sub I, where these are the boundary conditions on the domain, right? D. I will now say that this D could be integrated within the closed or bounded domain. So in mathematical terminology, we now say that such problems are also known as the boundary value problem, which we have looked up, okay? And the governing equations for these kind of problems are usually elliptic, okay? Okay? And then we now have another class of problem, which is the eigenvalue problem. And the eigenvalue problem could be thought of as an extension of the equilibrium problem, or better still, of the boundary value problem. Now you realize that when we consider the boundary value problem, we literally had to classify it in such a way that we mesh the boundary value problem and the characteristic value problem. So technically speaking, the eigenvalue problems are usually thought of as an extension of the equilibrium problem, such that the critical values of certain parameters are now to be determined in addition to the corresponding steady state configuration, okay? And that is why we now say that the problem is to find some constants, say lambda, and these constants actually are related to some function, say phi. So that the differential equation can now be described as L of phi being the same as lambda m of phi, where m of phi is the eigenfunction and lambda is the eigenvalue. And this also is satisfied within the domain D for the boundary condition B sub I of phi being the same as lambda E sub I of phi. Okay? And also the operators in this case for L and M are equally elliptic. Okay? That this is also of elliptic type. Okay, so far, well, we've been talking about elliptic. So we're going to talk about what this elliptic means shortly. Okay, we're just trying to classify based on what we've been doing. And now we also have one more, which is the propagation problem. I'll call these the initial value problems. Okay, and they equally have an unsteady state or some transient nature. Okay, so we say it's going all the way. So we cannot really say it's steady state, but there's some transient. So when we talk about unsteady or transient nature. So what is expected is to predict subsequent behavior of the system given their initial state, because it's not stable, it's not steady. Okay, and this is done by solving the differential equation like we mentioned earlier, say L of phi being the same as F. Still within the domain D, when the initial value is described as I sub I of phi being the same as H sub I. And this is also subject to some prescribed conditions, B sub I of phi being the same as G sub I. Okay? And the integration domain D, in this case, is open. So, just like I mentioned earlier, these propagation problems are also known as the initial boundary value problems. And the governing equations for these are usually called the parabolic, or better still, the hyperbolic type. So far, we've been able to look up the problems we have solved or been trying to solve, and some other problems you also have been trying to solve over the years, and you'll be solving in some other courses in this program. That, well, at some point, it's either what you are dealing with is, if we now have to come to dealing with multiple independent variables, it's either you are dealing with some elliptic type model or some parabolic type model or some hyperbolic type model. Okay, so this brings us to what we can now describe as the classification of partial differential equations. So we already mentioned that we have the hyperbolic, the parabolic, and the elliptic PDE, partial differential equations. Now, one thing I want you to take note of here is that these classifications is strictly based on the characteristic of the solution or of their solution. So in other words, you could have the characteristic equation that describes your model, and then the solution to that model based on some conditions may either make that model hyperbolic, parabolic, or elliptic. Is that clear, please? Did you catch that point?
No, sir. I did not get it.
Okay. Now, we just mentioned that in classifying partial differential equations could either be hyperbolic, parabolic, or elliptic. But now we are saying that the idea about being either hyperbolic, parabolic, or elliptic depends on the characteristic equation of their solution. And you already know what your characteristic equation is. Once you have your characteristic equation, you should be able to identify the poles of that equation. You should be able to tell the stability of that equation. So in solving that characteristic equation, whether it's a quadratic equation or it ends up, that's a second order equation, or better still, a third order or to the nth order equation, the solution to that characteristic equation will tell us what type of equation or partial differential equation it may be. So it means that a particular partial differential equation whose characteristic is defined may be hyperbolic depending on certain conditions. That same equation could be hyperbolic. It could be elliptic, depending on the properties of that characteristic equation. Well, it will get clearer when we look at a simple example. Okay? So what I'm trying to say is that the characteristics of their solution is primarily defined by a certain parameter, which we call discriminant, involving the coefficients of this equation. So this discriminant now provides a mathematical presentation that combines the coefficients of the characteristic equation. Now, this discriminant, whether it is, let's say we call it delta, whether it is greater than 0, or whether it is equal to 0, or whether it is less than 0, will now give us the information as to whether that equation is either hyperbolic, parabolic, or elliptic. Does that make sense now?
Yes, sir.
Okay.
Yes, sir.
Okay.
Doc, please, I have a question just to clarify. Can you explain again why we're introducing the discriminants?
Now, we are literally introducing the discriminant so as to be able to classify the equation. That's one. Okay? Because the discriminant of the polynomial, in this case, is a function of its coefficient, which gives us an idea about the nature of the roots or the direction of that equation. So at some point, you are solving propagation problem. You want to tell the direction of that propagation of that particular, of the propagation. Okay, so what's the direction? How many directions does it have? So the number of directions will now be determined by the number of roots in that equation. Okay, and the only thing that will be able to now give us that information that pulls the roots of that equation together is the discriminant. So the discriminant does not only tell us whether this equation is hyperbolic or parabolic, it's also able to tell us the direction of that equation or the number of roots we have in that equation, whether we have real roots, whether we have conjugate roots, or whether we have no roots at all. Does that address your question?
Yes, it does.
Okay. So if, for instance, we now have, let's say, second order polynomial, say ax squared plus bx plus c, for instance. So we have this simple equation, and now we want to figure out, okay, what can we tell about this simple second order differential equation? So how do we represent this? So who can tell us what the discriminant of this equation is? Can you tell us what the discriminant is?
Parabolic.
Yeah?
You say it's parabolic.
Is it now? This is quadratic, right?
This is quadratic.
This is quadratic.
The discriminant, if it's a quadratic equation, can you hear me, sir?
Yeah.
The discriminant is b squared minus 4ac.
Yeah, the discriminant is b squared minus 4ac.
4ac.
Perfect. That is the discriminant of this given equation, and we can actually assume or infer this from the quadratic formula, right? Now, if this is the discriminant, so it means that the given function, for this given function, the discriminant now tells us the number of roots it has. Okay? Is that clear, please? It tells us the number of roots this simple equation has. So if this discriminant, for instance, delta is greater than 0, so we know that this quadratic function will have two distinct real roots. What if the discriminant is the same as 0? So it means that this quadratic function will have one repeated real root. What if this discriminant is less than 0? So it means this particular quadratic function will have no real roots, largely because it now has two complex conjugate roots. Okay? Does that make sense? And when this and you can experiment that, you know, so you can experiment that, because when we now have a -1 for the square, so that's a j, right? So we're going to be having a complex conjugate root, right? Okay, so well, we don't want to go into all that right now. So let's leave that for the basic elementary mathematics. So now, when this discriminant is greater than 0, we say that this PDE, for instance, is hyperbolic. And when it is the same as 0, it is parabolic. And when it is less than 0, it is elliptic. Okay? So we are literally trying to scale down now. But there is a twist in this, because here we are dealing with a quadratic equation. What if we now have to deal with a second order partial differential equation? Okay, let us switch things now. So let's see what will happen to this discriminant. Okay. So let's assume we now have to deal with a second order partial differential equation. Say it's given by AU XS sub SX plus 2 EU XY plus CU YY. So here we can add some lower order terms, right? To be the same as 0. So we know that U sub XX just tells us that this is the second derivative with respect to X. UXY is mixed derivative. So we have the U, the squared U, the X, the Y. And then UYY is equally the second derivative, the squared U, the Y squared, right? With respect to Y. So what is going to be the discriminant in this case? Now, we already know for the quadratic equation, the discriminant is the same as b squared minus 4ac, right? So what is b in this case? B is 2, right? 2b, right? So let's say 2b squared minus 4. What is a? Is capital A, then c is c. So this is going to give us
4b squared.
B squared minus 4ac, so which is the same as b squared minus ac. So this is the discriminant, okay? Or just divide through by 2. So for the second order polynomial, we now see that the discriminant is of this form. And we already know that when this discriminant is greater than 0, we have a hyperbolic PDE. Okay? Largely because in this case, we have two distinct real characteristic direction this time. We are no more talking about root, right? Characteristic direction. Now, while we talked about the quadratic equation of function, we talked about roots. But now we are talking about the partial differential equation. We are talking about characteristic direction. Okay? So it means that this solution propagates as waves. That's the idea. They propagate as waves. So that is why such, okay, go ahead, please, Timmy. You can unmute and tell us. I can see your hand, Olani Timmy. We still can't hear you. I can see your hand up. Okay, so let's assume the hand just went up by default. Okay, so we'll go on.
Before it comes in, what is LDT in that equation, sir? The LDT.
Okay, so those are lower order terms. Lower. I just said lower order terms, right?
Okay, sir. Okay, lower order terms.
So if
sorry, sir. Can you hear me, sir?
You can say LOT, whichever way. Yeah, go ahead, please.
Yeah, sorry. Where's the 4 from the discriminant?
Where is the what?
The 4b squared minus 4ac. Like you did not put it in the last equation.
4 divided by 4, like divide both sides by 4.
Okay. Okay, sir.
Exactly.
All right, sir.
Nothing.
But it didn't affect the left-hand side.
No, that's just the discriminant. Okay.
Okay.
Yeah. And this is equal to 0, right? So all of this expression is the same as 0. For the characteristic equation to solve is equal to 0, right? So, isn't it? Okay.
Hello.
Now, okay. Any other comments?
Yes, sir.
Go ahead, please.
Yes, when we are finding the discriminant, are we not going to add the LDT's value in case?
No.
Okay.
They are not. They are not.
Okay.
Because here we are literally dealing with second order, right? Don't worry. I think things will get clear. Don't worry. Or you can literally strike this off. Okay?
0.
Yeah, I just say it's equal to 0.
Okay, sir.
Yeah. Okay.
I have a question, sir. So the particular discriminant we just got is for the condition that the discriminant is greater than 0, which is an hyperbolic PDE. In this case, are we also going to be looking at the other types, the parabolic and I think
Sure. We will. Now you see that in this case, we have two distinct real characteristic directions. So it means the solution of this equation, the solutions propagate as waves. And that's why we use this for wave equation, right? Like you all mentioned, it's a wave equation. So when we talk about wave equations, we know we are going to be solving hyperbolic partial differential equations. So for those of you that will be taking electromagnetic wave and the like, so once you may hear your wave equation, just know you're solving hyperbolic partial differential equations. Now, when the discriminant is the same as 0, we already mentioned that this is parabolic PDE. Here we have one repeated characteristic direction. So it means that the solution evolves in one direction, right? Not in multiple directions like the hyperbolic PDE. So it means solution evolves in one direction. And this is typical of heat equations. So that is why when we talk about heat equation, then what describes the heat equation is the parabolic partial differential equation. Okay. Now, what happens when we have this discriminant to be less than 0? We already mentioned that it is elliptic partial differential equation. And here we know that there is no real characteristic direction. Right? So if we do not have a real characteristic direction, then what could possibly be done in this case? So I need someone to give me an explanation.
Oh, come again, please. Don't be offended.
So now, in this case, there is no real characteristic direction. So interpretively, we are saying that the solutions are smooth and spread out, right? Solutions are smooth and they spread out. So if there is no real characteristic direction, it means we can't be talking in terms of propagation, right? We now have to look up solutions that are smooth and are spread out. So what equations can we say this describes? Okay, I'll just put it down, then we'll look them up as we progress. The Laplace equation and also the Poisson equation. Now we know the Laplace equation is the Laplacian of the function equated to 0. But when the Laplacian of the equation is equated to some function, then we say it is Poisson, right? So now we'll look at this, okay, and see that such equations or models are referred to as the elliptic partial differential equations. And now if we have to solve such partial differential equations, we know what we have to look out for. They're elliptic. Okay, they're elliptic. And if they're elliptic, then it means that we have to now try to figure out the numerical methods that best apply. Okay, so don't forget, this session is not a session on partial differential equations. It's a session on the numerical methods for partial differential equations. But interestingly, we have to figure out what partial differential equations mean, how we come across them, or in what form we come across them in our discipline as engineers, and then that will also help us appreciate whatsoever method we want to apply. Okay? So we can now say that the classification of hyperbolic, parabolic, and the elliptic partial differential equations plays a crucial role in understanding wave propagation, heat diffusion, and even steady-state field distributions. Okay, well, we now have to see very smooth and spread out solutions. Okay, so let us see if we'll be able to consider these cases one by one. So let us take the hyperbolic case, b squared minus ac being greater than 0. And in this case, let us consider the electromagnetic wave propagation. Now, you know so well that the wave equation is the same as the squared v, the x squared minus 1 over c squared, the squared v, t squared being the same as 0. So you now see that we have the spatial component x and the time component t. So this wave equation literally describes electromagnetic wave propagation either in free space, in dielectric, or even transmission lines. And we know that the solution will be some traveling waves, right? So now, if we say that the solutions are some traveling waves, we are literally saying that the signals of fields propagate without attenuation in ideal conditions, right? So that is one. Now, we can also look up another interesting second-order hyperbolic partial differential equation, which is the Maxwell wave equation, okay? Where we say Nambla squared E, which is more like the Laplacian of the electric field, minus 1 over c squared, d squared E dt squared is the same as 0. And we know, for those of you that engage in communication activities, we know that this equation governs radio waves, microwaves, and also optical signals. And we also use this for antenna design, radar systems, and even wireless, excuse me, wireless communication. The bottom line is that in considering this second order partial differential equation, given the discriminant to be the same as b squared minus ac being greater than 0, that this Maxwell's wave equation literally describes or connotes an example of a hyperbolic partial differential equation. Now, we also have another example that describes lossless transmission line equations, okay? Where we have the squared V, dx squared minus LC, that's your inductor capacitor, the squared V, dt squared being the same as 0. So this equation literally models propagation in coaxial cables, even microstrip lines, and also optical fibers. And what does this do? Since we are literally talking in terms of lossless transmission, it means it ensures minimal distortion for high-speed digital communication, right? Okay, and these are all examples of hyperbolic equations that we play with from time to time in our engagement. So let's look up parabolic, where we now have b squared minus ac being the same as 0. An example is the heat diffusion equation, okay, where we have the v, dt minus d, the squared v, the x squared being the same as 0. Now, this diffusion equation literally models heat conduction and signal attenuation in lossy media, right? Heat conduction and signal for the heat diffusion equation. So this is heat diffusion. Okay. So we also have another interesting example, which is signal loss in conductors. And here, when considering lossy transmission lines such that the V, the T is the same as the squared V, yeah?
So before you,
go ahead, please.
Sorry for interrupting you. Before you go further, can we also use this equation, the first equation, as in dv dt minus d dv squared dx squared for heat conduction in cables, as in power systems?
You mean the electromagnetic wave equation?
Yes, this first equation for heat conduction in cables.
Yeah, but what are we talking about here is heat conduction. And that's what we just brought up here now, where D is replaced by RC.
Okay.
Right? So now we are literally considering a lossy transmission line. Okay. And then we say, well, we could use this for submarine cables, and especially where the resistance causes energy dissipation, right? So we know once we have our resistance, then there must be some dissipation of, heat based on resistance to current flow. Okay, so, and here we now have to play with parabolic equations. We also have, for those of you that are conducting your research in thermal management, when we talk about power electronics, so we also have the T minus K, the squared T, the X squared is the same as 0. And here we are literally describing the heat spreading in semiconductors, heat sinks and transformers, right? Okay, but whichever way, if you have to do this, then what we are literally dealing with are parabolic partial differential equations, okay? And then we also have the elliptic case, just trying to pull off some examples that you see in your day-to-day activities, where we now have B squared minus AC less than 0. And here we could consider both electrostatic and magnetostatic fields. Okay, so when we consider electrostatic and magnetostatic fields, then the Laplacian equation or Laplace equation, that is the squared V being the same as 0, now governs the steady state electric and magnetic potential distribution. And here you realize that while we are talking about potential distribution, we are not talking about propagation. Okay, so I leave that for your technical studies in some other courses. And we also have another interesting example, which is electrostatic potential in capacitors. Electrostatic potential in capacitors, where we have the squared V, the X squared, plus the squared V, the Y squared being the same as 0. Okay. Now, this is literally used in capacitor design to calculate the electric field distribution. Okay. So, and this could also be used in high voltage insulation and PCB designs. And one more example is when we consider magnetic fields in transformers, okay? Magnetic fields in transformers, okay? And here we now have to play with the Poisson's equation, or Poisson equation. So rather than have this to be the same as 0, then it means it's now the same as some other parameter. Say the Laplacian of A might be the same as minus mu J. Okay. So here we want to compute the magnetic vector potential in the electrical machines. And we also use this for designing transformer motors and insulators and all of that. And what we are not dealing with here is we are not talking about propagation and all of that. We are literally talking about the elliptic partial differential equations. So you will observe from all that we have talked about, a little distinction between the quadratic polynomial and the second order partial differential equation discriminant. Okay, so we had B squared minus 4AC for the quadratic polynomial. And then we have now delta being the same as b squared minus ac for our second order partial differential equation. So in the case of the quadratic polynomial, the discriminant literally determines the nature of the roots of this equation, okay? But in the case of the partial differential equation, the discriminant literally tells us the nature of the characteristic curve, right? And consequently, the direction, okay? So what this tells us is that this classification will now help in understanding how the solutions either propagate and whether they resemble a wave or a diffusion process or some steady state solutions. Is that okay? Now, so that when you begin to solve your engineering problems in your field and you now begin to deal with multiple independent variables, you also want to figure out the solution to the discriminant to know if it is less than 0, if it is equal to 0, or if it is greater than 0, so as to know the type of partial differential equations you'll be solving, and then you'll now be able to position such applications accurately. Okay? Now, let us consider a cubic polynomial, for instance. So we've talked about second order, right? So what if we have something beyond second order? How do we establish the discriminant? Let us look at that. Largely because, well, we try to keep the lecture series as simple or simplified as possible. But the truth is, when you begin to model practical systems, you now realize that, yes, in engineering, most of our solutions, kind of converge within the second order differential equations, okay? We're talking about the Laplacian and all of that. But we also have the higher order equivalent of this Laplacian or Poisson or Laplace equation, Poisson's equation, and the likes, okay? So that depending on how complex the system you now want to analyze or develop or design may be, you may run into a system of equation that may run into higher order polynomial or higher. So when you run into that, when you now have to solve higher order polynomials, how do you resolve that? Then how do we come up with the discriminant, the quadratic formulation may not subsist. It will not. Okay, so let's just look at a few examples and then see how we could quickly run through some of the numerical methods. Okay. So if, for instance, we are given a cubic polynomial, say x cubed plus bx squared plus cx plus d being the same as 0. So what could possibly be the discriminant here? Can anyone help us out? Okay, so, well, there are so many ways we could do this, okay? There are so many methods, but I'll just pull off one method while I leave other methods for your research, okay? So now we could use the Sylvester matrix to do this. And once we do that, it's an interesting method because it comes from the greatest common divisor by the polynomial and its derivative. And then we just develop a system of matrices for that and then solve the determinant. Well, will I call it a crude method? But, well, so long it works, we are fine. Okay. So if P of X is the same as AX cubed plus BX squared plus CX plus D, then the first derivative of this will be 3A x squared plus 2bx plus c. So now we can develop the Sylvester matrix from this to say, well, S is the same as the coefficients. We pull out the coefficients A, B, C, D, and then we repeat A, B, C, D in this case, because we want to come up with a 5 by 5 matrix. And then we have 3A, 2B, C, 0, 0. Then 3A, 2B, C, 0. Then we have 3A, 2B, C, 0, 0. So now, once we find the determinant of this, this is going to give us the discriminant. And now we see that the discriminant of this will be the same as 18abc minus 4b cubed d plus b squared c squared minus 4ac cubed minus 27a squared d squared. This becomes the discriminant, okay? Well, there are other methods in the literature that you could look up to address this, okay? So if that is that, so it means that for the cubic, bx squared plus c, x plus d being the same as 0, the discriminant is the same as 18abcd minus 4b cubed d plus b squared c squared minus 4ac cubed minus 27a squared d squared. So let's assume you try to model a particular system, okay? And after modeling that particular system, you run into the third order polynomial. So in addressing the third order polynomial, you now want to establish the type of partial differential equation that system really represents. So you want to figure out the discriminant. And then in this case, we see that when the discriminant is greater than 0, we see that the cubic function has 3 distinct real roots. So meaning for the third order partial differential equation, we have 3 distinct characteristic directions, right? And when the discriminant is the same as 0, then we see that the cubic function has multiple roots. With at least 1 repeated root. And then when the discriminant is less than 0, we see that the cubic function has 1 real root and 2 complex conjugate roots. Okay. And once again, just like we established earlier, when the discriminant is greater than 0, we know we are dealing with some hyperbolic-like behavior. And when it is the same as 0, we are dealing with some kind of parabolic-like behavior. And when it is less than 0, we are dealing with some elliptic-like behavior. So that when we now have the hyperbolic-like behavior, then it means that the characteristic equation has three distinct roots. So the partial differential equation will now have three real characteristic directions. Now, this simply means that information propagates along three independent wavefronts. That's what it means, okay? So if, for instance, this is a hyperbolic system, PDE, then it means that in this case, that information propagates along three independent, right? Three independent waveforms. So we are literally looking at some form of nonlinear wave equations, okay? So we are moving from linear to nonlinear this time. So you now want to resolve some form of nonlinear wave equations, more complex, okay? Good for research anyway. And now for the parabolic-like behavior, we know that the characteristic equation has at least one repeated root. So it means that the partial differential equation has a degenerate characteristic structure. That means that at least one characteristic direction is repeated or is missing. So we say it's degenerate, right? So this also deals with some diffusion type of processes, okay? So we want to generalize the heat equation. And then we have the elliptic type, where we know that, okay, in this case, the characteristic equation has at least one real root and two complex conjugate roots. So interpretively, the partial differential equation does not have three independent real characteristic directions. So it means that the solutions behave more like the elliptic equation. They are smoother, but no real wave propagation in this case. So here, just the same way we were able to use this to address steady state equations. So we'll still be addressing steady state equations. And then the Laplace-like equations and the Poisson-like equations will now apply. So when we talk about numerical methods for partial differential equations, we have the hyperbolic, which are the wave-like equations. So we already know that they have sharp wavefronts, they propagate along the characteristic. So some of the methods that may apply are the explicit finite difference method. And there we want to consider the likes of the Laps-Wendroff. We also want to look up the leapfrog and also the Upland for the finite difference method. Then we also have the finite volume method. And then we have the spectral method. Now, why do we select these methods among all other methods? Now, we choose them because of their level of accuracy in terms of capturing wave propagation. They are also capable of handling shocks well, and they equally avoid dispersion. And then there are some other methods, okay, you want to also explore. Then we have for parabolic model, where we talked about the heat equation. And now for this, we understand that the behavior of the system is diffusive. Okay, so we need some kind of smooth solutions over time. Then you want to look up implicit finite difference method. And here, you want to look up the Frank-Nicolson. Then we have the backward Euler methods. Then we also have the finite element method. And we also have the method of lines. Now, why do we choose these methods for parabolic partial differential equations? Because they ensure stability, okay? And they also allow larger time steps. The explicit methods, where they allow, smaller time steps. So we want to use the implicit methods largely because we may be needing larger time steps, and they also handle complex geometries, okay? And they equally ensure stability. Then, for the elliptic method, where we now have to play with the Laplace and the Poisson methods, we see that we can apply the finite difference method here using iterative solvers. We have the finite element method. We also have the spectral method, and then the multi-grid method. Now, why do we prefer these methods for elliptic partial differential equations? Well, they efficiently solve global equilibrium problems because we are talking about steady state solutions, right? So these methods work well, for irregular boundaries. So, but are they the best? Well, they're okay, they're fair, but based on looking up some of the reasons we just mentioned, you want to play with them. And interestingly, we've played with finite difference method. We've played with finite element method in our previous lectures. So we'll just look through them and then see if we'll be able to solve some problems if we've got some time. And if not, then you want to solve a few problems in your spare time. Okay? So let us look at the finite difference method. Now, the finite difference method for solving partial differential equation literally discretizes both the space and the time derivatives, because now we are dealing with it. Now, when we played with ODEs, we literally discretized just a single independent variable. But this time we are going to discretize two. But for us to be able to play with this, we have variants, okay? We have the forward difference approximation. We also have the backward difference approximation in terms of discretizing the partial differential equation. Then we also have the central difference approximation. So we'll just provide the formulation for this, okay? So let's provide the formulation for the forward difference approximation, then we'll do same for others, okay? Now, if we assume, let's take U of ST to be the function of both space, it's a function of space, x, and time, t, with some step size, delta x, and delta t for both the space and time variables. Then for the forward difference, approximation, if we have a first order, let's say we have a first order partial differential equation. So we're going to discretize the time derivative to be approximately the same as u of xt plus t minus u of st over dt. And the space derivative, the u, the x, will be approximately u of x plus the x t minus u of st dx. So I want to believe, should you have the second order, third order, even to the nth order, you should be able to do so. But let's look up the second order discretization process. So what if we have the second order? In this case, we are looking at the forward difference approximation. So it means that the squared u, the t squared, will be the same or approximately the same as u of xt plus 2 delta t minus 2u x comma t plus delta t minus, or no, plus u of st over the t squared. Then to discretize the second order space derivative, the x squared will be approximately the same as u into brackets, this time x plus 2 dx comma t minus 2u x plus dx comma t plus u of st squared. Now, the same also happens for the third order, okay? So, but now let's just put up the nth order, okay? Using the binomial distribution, forward difference approximation. So it means that the n, u, the Tn will be approximately sigma, or better still, let's just conserve our space. Will be 1 over Tn sigma k equal 0 n minus 1 k n combination of k u x t plus k dt by the n u the xn will be approximately 1 over delta xn sigma k equals 0 to n minus 1 k in combination k u. This will be x plus k dt. The x rather, that's for x. X plus k dx is t plus k dt, comma t. Okay, so that's for that. So in discretizing, so it means that when you are given the partial differential equation, you first want to discretize it, then you solve. Just the same way we played with the ODE. Or if we have some time, we'll look at a few examples. And then we have the backward difference approximation technique for the finite difference method. So we also have for the first order, the U, the T is approximately U of ST minus U of X, T minus dt over dt. And we have the U, the T, the X rather, is approximately U of xt minus U into bracket X minus the X, then T over the X. Now, what if it's second order? So we have the squared U, dt squared is approximately U of xt minus 2U into bracket xt minus dt plus U of xt minus 2 dt over dt. And then we have the squared U, the x squared is approximately U of xt minus 2U s minus the xt plus U x minus 2 the xt over the x squared, that is squared, second order. Okay. Now, okay, just before we move on, let us look up the third order. Okay. Now, for the backward difference approximation. So that will give us the Q, U, the TQ is approximately U of ST minus 3U. It's more like some form of binomial expansion, right? ST minus delta T plus 3U into bracket XT minus 2 delta T minus U ST minus 3 delta T over the TQ. And then the cube U, the X cube will be approximately U of T, U of ST as a function, U of XT minus 3U of the X minus the X T plus 3U S minus 2 delta S T minus U into brackets X minus 3 dx T over delta X cubed. So that the n U, the Tn will be approximately 1 over delta Tn sigma k being the same as 0 to n, and it's 1 to the k, and combination k, U, x, t, minus k, t. And the n u, the t, the x n will be approximately 1 over the xn k equal to 0 to n minus 1 to k and combination k u x minus t the x t. Then another method for discretization, which is usually considered to be more efficient, is the central difference approximation. Okay. So let's assume we want to use the central difference approximation. Now for the first order, we have the u, the t is approximately u of xt plus the t minus u of x t minus the t over 2 beta t. And for the u, the t is approximately u of x plus dx t minus u of x minus the xt over 2 dx. So the second order also follows directly. So the u, the squared u, it is squared, yeah, approximately u xt plus dt minus 2u st plus u st minus dt over dt squared, and the squared u, the x squared will be approximately u x plus the xt minus 2u st plus u x minus the xt over the x squared. Now we can literally go on, and then even to the third order, but let's just describe the nth order for the central difference approximation. Now have the nu, the Tn will be approximately 1 over delta Tn sigma k being the same as 0 to n, and combination k u xt plus n minus k t n u xn will approximately 1 over delta xn sigma k will be same as 0 to n minus 1k and k u x plus n minus 1 x. Okay. So you now see that here we have different approximation techniques: the forward difference approximation, the backward difference approximation, the central difference approximation for the finite difference method. So how do we choose a particular approximation technique? Okay, so you now see that for the forward difference approximation, we mainly use this for the explicit.
Sorry, before you go forward, the nth order for the x, is it n minus k or n minus 1?
Which of them?
The nth order for the x, derivative of.
No, this minus k, please. It's minus k. It's just the same, right? That's minus k. So here is x plus 5. This is x, then t, then it's k, please. Thank you. Okay, so when we want to model explicit time matching schemes like forward Euler, we use forward difference approximation. So we'll see some examples anyway, not to worry about for now. Then for the backward difference approximation, they are mainly used for implicit methods. Or we consider methods like backward Euler, although they are more stable for stiff problems. And then for the central difference approximation, we mainly use this for partial derivatives in wave equations. So if you want to look up the wave equations, diffusion equations, even the Laplace and Poisson equations, because of their, accuracy. Okay, they have better accuracy. So bulk of the partial differential equations we'll be playing with if we want to rely more on the central difference approximation. But not that we don't use others, we also use them. Okay, you see how we get to use them. Then, okay, we are running out of time already. So this is one interesting method. Then we also have the finite element method, which we talked about earlier. We have a spectral method, We have the hyperbolic method, and on. Quite a number of methods that we mentioned. And bulk of our examples, we try to use the finite difference method to solve them. And there are quite a few examples solved here. If time permits, maybe we'll solve them, but I'd love you to now look up some of the examples in your recommended test and see which and which are able to lay your hands on as you progress.